Hi, my name is Pitt Henrich. I'm presenting our work titled Tracking Tumors under Deformation from Partial Point Clouds Using Occupancy Networks. This work is part of a collaborative project between the Spark Lab at the Friedrich-Alexander University Erlangen-Nuremberg and the Immerse Lab at Johns Hopkins, and also the Department of Urology, also from Johns Hopkins. We understand tumor tracking to be the problem of localizing tumors inside of a deformable object. An application example is the robotic-assisted partial nephrectomy. Therefore, the removal of parts of the kidney, for example, to remove tumors. The tumor positions are known during the medical imaging processes, but during the surgery, the organ and its embedded tumors will move and deform. So the problem we're approaching is, given a surface point cloud of a deforming kidney, from a depth sensor, for example, obtain the kidney orientation and the tumor locations. And importantly, we want this approach to be fast, so that a downstream robotic system doesn't have to wait on the localization. We approach this problem using neural occupancy networks. These occupancy networks can learn the shape of 3D objects conditioned on some input, for example, a surface point cloud. We use this ability to learn the shape of deforming kidneys given a single-view surface point cloud observation. In this diagram, we show a hydrogel phantom with 2 embedded tumors. Using a CT image of the phantom, we extract triangle surface models. We then apply random deformations to the surface model and obtain a single-view surface point cloud using a virtual camera. Simultaneously, we create a dense occupancy point cloud of the deforming surface model. In the occupancy point cloud, each point encodes the segment, if any, it is inside of, so the kidney, tumor 1, tumor 2, or outside. The pairs of sensor point clouds and occupancy point clouds are then used to train the occupancy network. By learning to label the occupancy point cloud conditioned on the sensor point cloud, the occupancy network learns the shape of the deforming phantom. To measure how well our system is able to estimate the position of the tumors and the orientation of the kidney, we use a setup shown on the right. To create the dataset used in the evaluation, we deform and rotate the kidney phantom. We then capture a surface point cloud using a depth sensor, which will be used as the input to our occupancy network. Additionally, we capture a CT image to obtain the ground truth shape of the phantom. Finally, here's a small look at some results we obtained using a single frame from a low-cost depth sensor. Additionally, the training data was created without a physics-based deformation model. Both of these limitations need to be addressed in future work. To generate an output, we query the occupancy network using random query points, giving us a labeled occupancy point cloud. It takes approximately 16 milliseconds to produce an output, as shown on the left. We evaluate the accuracy using a denser reconstruction of the kidney phantom, which is then compared to the reference CT image. On the right, you can see the input point cloud obtained from our low-cost depth sensor. After it, the output of the occupancy network given the input point cloud. Third, we see the ground truth shape of the phantom obtained from the CT image. And finally, we see the estimated and the real tumors and the reconstruction error, where blue is an over-reconstruction and orange is an under-reconstruction. We found that with our current approach, we can estimate the tumor positions and margins for moderately deforming phantoms to within a few millimeters, as indicated by the centroid error C and the Hausdorff distance H. For reference, the kidney itself has a total width of approximately 140 millimeters. Thank you.